Good morning, algebra. So we are learning about solving exponential equations. Remember, exponentials are equations in which the variable expression occurs as an exponent. And we saw this with our growth, why can't I think of it? Growth exponential and our decay rate, growth function and decay functions. We talked about how growth is like a bacteria colony, excuse me, or the pandemic, or a savings account, compared to decay, which is like radioactive decay or the devaluing of a car or a house, sometimes even, depending. Usually house properties go up, but there are times when they decrease, back in like 2008, for example. So this week we are looking at, well, how do we solve exponential equations? How do we solve exponential equations? Now remember, exponential equations have a base and they have an exponent. The exponent is going to be where the x is for an exponential. So when we want to solve an exponential, it's really important to know that the base of one that has a certain exponent is going to be, if they have the same positive base, their exponents have to be equal. So if we have two bases and they have exponents, they must be the same. They must be equal, right? They have to be. Let me show you what this means, because I know just saying that is a little weird, right? What does that mean? Well, right here we have a 3 and a 3. One is 3 to the x plus 1. The other one is 3 to the 5. Both of those bases are the same. They're 3, right? Well, if the bases are the same and they're equal, then the exponents have to be equal as well. So that means that this x plus 1 and this 5 have to be the same. So I can say x plus 1 is equal to 5, right? So we kind of see that here with this 2 to the x and the 2 to the 5th. We know that if we have 2 to the x and 2 to the 5th, then x must equal 5 for the other guy. So in this case, we had 3 to the x plus 1 and 3 to the 5. So x plus 1 has to equal 5. And now it's like any other algebra problem, and we can solve it. I need to get x by itself. I subtract 1 on both sides, so I get an x is equal to 4 in this case, right? Because 5 minus 1 is 4. So we can do that with any of these. We're going to do a couple more. The one thing I want you to know, that I want you to have in your mind, in order to solve these, we need to make same bases. All right, and we'll get to some of that. It's not on this side. It'll be on the next side. But we'll do some of these for a little while. So for this next one here, we've got 6 equals 6 to the 2x minus 3. Now, we know what our one exponent is, but what's the exponent on this first 6 here? He's a ninja. Yeah, it's a 1. There's a 1 there. So our bases are the same. That means I can do 1 equals 2x minus 3. I need to get x by itself. So I have to add 3 on both sides to start. So 4 equals 2x, and then I divide by 2. So we have 2 is equal to x. I highly encourage you to do a check on these to make sure that that makes sense. So if we plugged 2 back in, we would have 2 times 2 minus 3. Well, that would be 4 minus 3, so that's 1. Does 1 equal 1? Yes, it does. All right, so for our next one here, we've got 10 to the 3x equals 10 to the 2x plus 3. We want to pick out our exponents, which are the same. Our bases are the same, right? They're both 10, so that's great. So we have 3x equals 2x plus 3. I'm going to start by subtracting 2x on both sides, because it's always good to start by moving the x's. So we've got 1x is equal to 3. Another way of saying that would just be x equals 3. That might be another way of saying it. So yes, that works. It's great. It's awesome. All right, I'm going to switch over to the back side. Okay, I'm going to switch over to the back side. I want you guys to try these 3. Try these 3. All right, so for this one, hopefully you pause the video. For this one, you should get an x equals 3. For this one, you should get an x equals 1. And for this one, you should get an x equals negative 2. All right. What happened to my backside? Here it is. All right, so sometimes we'll come across things where we don't have the same bases. If they don't have exactly the same bases, then we can't do anything about it. But there are times when we can rewrite a number so it is the same base. And I'm going to start up here with this one. All right, so we've got 5 to the x equals 125. 125 is actually not prime. All right, it's not. So we know that it's going to have multiples of some kind, right? Of some kind. So in this case, if you take a look at that chart that we did, the tables, right, of the 1 powers and the 2 powers and the 3, if you take a look at it, you will see that this is really 5 to the 3rd power. Hey, wait a second. If this is 5 cubed and this is 5 to the x, then I have the same bases now, right? Now we have the same bases. Once we have the same bases, we can solve these. Until they have the same bases, we can't. So we've got an x is equal to 3 now because our bases are the same. All right, I'm going to jump over here and do this one next. For our first, or left side, I should say, we've got 9 to the x plus 2, and then on the right, we've got 27 to the x. Now take a look at your chart again. You'll notice that 9 and 27, neither of them is prime, actually. So both of them we can change, all right? So we know that 9 is really, and I'm going to do it this way, all right? Nine is really 3 cubed. Squared. 27 is really 3 cubed. Hey, look at that. I've got a power to a power here. I know. We learned all those rules for a reason. It's great. So a power to a power says that I need to multiply that out. So I'm going to leave my 3 inside my parentheses here. The 2 is going to come on the outside, and then I'm going to put parentheses around this guy. Why am I doing that? I'm trying to help you see how we are going to use the power of a power. So if I look at these, I've got the same base now, right? So really what I have is 2 parentheses x plus 2 is equal to 3 parentheses x. And that's really, really important. All right, that's really, really important. Because I need to distribute that 2 and that 3. Well, on the 3 side, it's pretty easy, right? 3 distributed to the x is just 3x. On this side, though, it becomes 2 times x, which is 2x, plus 2 times 2, which is 4. So if I subtract 2x on both sides, we end up with an x is equal to 4. All right, I'm going to skip over some of these. I want you guys to try these out, all right, these next 4. This one I know you can't see, so I'll show you for just a sec. So it's 4 to the 3x equals 8 to the x plus 1. I would recommend that you take it all the way down to 2. Okay, change those into 2s. Anytime you see a 4 or an 8 or a 16, it's easier to just change it into 2s. All right, so for this one, you should x equals negative 3. For this one, you should have gotten an x equals 4. For this one, an x equals 2. And for this one, an x equals 1. If you want to see those problems actually worked out, please go check my note key. All right, please go check my note key. So this is the one that I wanted to jump down to because some of you are going to look at me and go, well, I can't solve it. I mean, it's a 4 to the 2x plus 3 and a 1. I got nothing. How do you do that? I want you to remember that anything to the 0 is equal to 1. Right? So if we need a base of 4, I'm going to rewrite my left side so that we have 4 to the 0. Because it equals 1. Hey, look at that. We got 4. We got 4. Isn't that great? So 4 equals 2x plus 3. So now that I have the same bases, I can just look at the exponents. So 2x plus 3 is equal to 0. So I'm going to minus 3 on both sides. So we have 2x equals negative 3. And then when we divide by 2, we get an x equals negative 3 halves. Sorry, I couldn't see that for a second. All right, I'm going to do this guy next. Actually, I'm going to help you with him a little bit because 243 here is really 3 to the 5th power. Giving that one away a little bit, but I only did a chart to 4, so I'm going to scoot this guy so that we can see the rest of them. These ones down here are a little bit tricky. All right, these ones down here are a little bit tricky, so we can do those ones together. All right, if we look at this far left one, we have 2 to the x divided by 2 to the x and equals 2 to the negative 2x. First thing we need to do is we need this to be just one base. Well, we can't have multiple. We need it to be just one, all right? That way we're not having to deal with all of our rules. So we know that the power of a quotient is where we subtract our denominator exponent from the numerator. So I get x minus x, and it's equal to 2 to the negative 2x. Well, x minus x is really 0. So we really have 0 is equal to negative 2x. So when I divide by negative 2, we get 0 is equal to x. So in order for these to be equal, x would have to be 0. That means both sides would have to be essentially 1, right? Because anything to the 0 is 1. All right, with this one right here, I want to help you rewrite it. All right, we've got 1 over 10. In order to move him up so that we have, I know we like to have simplified exponents. I do know that. However, we need everything to be in the numerator. If it's in the denominator, we really can't solve it. It has to be in the numerator because these are in the numerator too. So when I move him up, he's going to turn into a 10. His exponent currently is a 1, so it would be a negative 1. And then for this side, we've got power of a product, so I have to multiply these together. No, add them together. Excuse me, add them. So this becomes 10 to the negative 3x plus x. So I really have negative 3x plus x equals negative 1. This is really negative 2x. So when I divide by negative 2, I get an x equals 1/2. All right, there are 2 more on here. One of them has to do with the 6, and the other one has to do with the 3. I'm going to give you a second to practice on those ones. All right, practice. All right, the answer to the 6th one is m equals 0. And the one down here is an x equals negative 2/3. Couldn't see that, my bad. Hopefully you found this helpful. This is typically one of the things students really enjoy about this chapter. Email me if you have any questions. And this is not on the test.